Okay, these are the where A, B very much greater than a current of variable current. Let me send it. Let R be the resistance of this. This resistance, I'll bring it here. No. The diagram shows concentric loops A and B. With current in inner loop varies as I equal to 2t square. Find the current through capacitor at steady state. So one instruction, neglect self-inductance of larger loop. Now carry on. This will call loop 1. There's a loop 1. There's a loop 2. Will there be any EMF induced in the loop 2 due to varying current in the first loop? Look at that conditions given, B very much greater than A. Now first, we should calculate the mutual inductance between them. How to calculate mutual inductance? I will jump to the let's get into the discussion here. So there's the inner loop. There's the outer loop. The resistors, capacitors I'll bring later on. Let's send a current here, say some high that one. Will it produce any magnetic field at the center of the loop? There's a loop 1. There's a loop 2. So what is the magnetic field produced at the center of loop? Mu naught I by 2b. Flux linking the loop. B2, I'll write it better. We'll use symbol. I2. Yeah. Flux linking the inner loop should be equal to B2 into pi a square. Mu naught I2 by 2b pi a square. Then how you define mutual inductance? Mutual flux linking the inner loop due to current in the outer loop. That should be equal to mu naught pi a square by 2b. Now one question like, okay, sir, what is this magnetic field? Can you tell me once? The field strength at the center, but the magnetic field at different points will be different. How come you're assuming the magnetic field everywhere inside the loop to be constant? Because what you found out, this equation is at the center, magnetic field at the center of the loop, mu naught I2 by 2b. But will it be magnetic field everywhere same? Look at this condition given. The size of inner loop, the radius of that so small that what is the field strength at the center, that will be same everywhere inside the loop, inside inner loop. I think this assumption is very important. What you calculate magnetic field strength at the center of the loop, that is going to be there, same value everywhere inside the inner loop. So the EMF induced. Okay, now we got mutual inductance. So can we calculate EMF induced in the outer loop? Do we know mutual inductance? It is mu naught di1 by dt, di1 by dt. So what is I1? So this should be equal to 4t. Okay, now we are in a better position. So there will be a cell, capacitor, there's a resistor. Very calculatively we have to work out here. The question. So this E2 we know it. So now he's asking find the current. Okay, let's write the equation. Q minus Q and the current I will flow. These are the polarities. So the equations will be plus C2 sorry, high. So what is the problem? I think this everything is a big constant. So I'll bring K. Every time writing this will be a big headache. We wanted expression for current here, no? Shall we differentiate here? Again, once again, this will be K minus 1 by C. I think this can be solved very easily. At t equals 0, what was the current? 0 at any time t, let I be the current. I think, okay, we are in far better position. We can work out now. 0 to I. What can be? Kc. Now look at this. It's asking steady state current. What shall we do at t equal to infinity? We had some basic idea. What is that? A steady state capacitor open circuit current will be 0. So one option will be there, 0, so that you can pick up and go wrong. Look at the cell. If the EMF of cell varies with the time, then the steady state current will not be 0. There'll be continuously there'll be flow of current. Just to make students to go wrong, because maximum we did so many problems at steady state, current through the capacitor will be 0. So maximum students open options will be 0 there, they'll pick up 0. That's all. They don't think anything. So we'll write it here. Steady state current. We do get plenty of questions based on this mutual inductance. This will be our answer. The more troublesome, this is what actually, because the current flowing here, how to calculate the flux linking the outer loop, I think you'll land in a big trouble. Since the idea of mutual inductance, you bring it. Let's assume that a current flowing in the outer loop, and then we'll calculate flux linking the inner loop, then flux linking the inner loop to the current in outer loop will give mutual inductance. Then we are proceeding here. But students, they don't think this one. They directly want to find out how to calculate that one. Not possible. Same thing here only. If I send a current I in this, what is the EMF induced in this wire? Can we find out? Yes, we can find out. But what is the problem? Can we find out the flux linking the wire due to current in this? Mathematically, we cannot find out. So what shall we do? Let's assume that a current flowing in this will calculate flux linking this, will calculate the mutual inductance to trouble you. In most of the numericals, if a current flowing in one loop, flux linking other loop, you can find out. But in either way, not possible. It's like a current flowing in long wire, due to current flowing in long wire, flux linking the loop, we can find out. If a current flows in this wire loop, then what is the flux linking the wire, we cannot find out. Don't say it will not exist. We don't have mass to find out. Let's come to the problem. Yeah, it's here, we are here. Let's have one more. So let's take a situation.